He works on use kind of groupthink to do various things in helping control, including autonomous vehicles as well as UAVs too. So just a perfect guy to talk tonight, and thanks so much, Chris, for being on your schedule. He also builds upon this has been Santa Clara University, half or quarter or millennium. We've gone on John Montgomery quite a bit and had some professors talk, and so I think it's fitting into our year's program to have Professor Christopher Kitts come talk to us. So, Christopher.
All right, well, thank you very much. I appreciate the invitation and the patience in going back and forth and trying to figure out what I can get here. But you had to know I was going to make it because my boss came and told me that I should come here and be involved. So, yeah, that would be great, actually. Also, before I start, I should point out that as you're going to see, I do a lot of hands-on work. I believe engineering is a practicing art, and if you're just sitting in front of a computer and doing analysis, then you're challenging the word engineer. And so the kinds of stuff you're going to see is trying to do a good job of applying the engineering sciences, but at the same time to physically test it and evaluate it and do things in the field. And we have a whole generation of kids who are not like this young man back here, which is unfortunate because I'm very impressed with your interest in doing these kinds of things. And we have a lot of kids coming to college who are afraid to touch anything and to get involved. And I appreciate just looking at what's going on here, the modeling skills and the craftsmanship that's going on, and a completely different effort that I've been trying to get going at Santa Clara, and Godfrey Mungle, my dean, is a huge supporter of this. You probably heard of Maker Faire and the Maker Movement and do-it-yourself kinds of stuff. So we've got our own, just in the past year, sort of maker lab with some rapid prototyping machines and laser cutters and hand tools and things like that. And it's not to say we don't have a beautiful set of laboratories across all our departments, but the inertia that it takes to get into those labs and the formal training you have to go in to go use the machine shop is so significant that if you just want to go in and do your own project, you can't. And so we're trying to lower the barrier of entry for people who want to get in and tinker and learn through doing. And I'm just really impressed by the stuff that you're all doing. And I could swear I think there's a ham radio going on here somewhere else, and so we're doing the same thing with RF kinds of projects as well. So I just want to give you an idea of the kinds of things we're doing. I run a robotics program at Santa Clara. I'm in the mechanical engineering department, but I advise students in mechanical, electrical, computer, and bioengineering. Occasionally we'll get some civil engineers based on the applications we do. But I would really want to sort of punch the notion of field robotics, and there are only a few robotics labs in the country that use the phrase field robotics to describe what they're doing. And when they say that, what they mean is that we do more than just the analysis and the simulation and maybe build a robotic device and operate in the corner of the lab under very nicely controlled conditions and calibrations, all that kind of stuff. But some of us want to actually take that technology out into the field where it's dirty and you can't model it and it's dynamic and things are changing. And part of that is I just love to get out of the lab, but to take this technology out and do real things, get feedback about what doesn't work very well that you thought might work well in the simulation. And the particular twist that we have is we develop our technology and our robotic systems to go out and do this, and we get paid to do it. So I support my program 100% through external funds, and some of that is research grants, and we do some interesting research, but a lot of it is we basically provide services to a lot of other companies and government agencies by building interesting robots that can do sort of specialty data products, if you will. And we go out and run them, and they're great design projects. They're challenging engineering projects, so even at the graduate level in terms of some of the research that we bring to bear on the problems makes it interesting. But we go out and we put underwater robots under the water with the Navy and U.S. Geological Survey and NOAA, and we operate spacecraft that we build or that NASA builds. We control them, and that's pretty darn cool. And so we get to incorporate the learning by actually running real missions that generate real data or do services, and we are, in essence, measured in how well we do it by the ability to sustain our program over time. So, next slide. So just real quick, a little bit of background in the lab. One of the interesting things we do is MultiRobot Control. So if one robot is good, then more must be better. And so we have a certain research take on that, but we're now starting to provide services with real robots that we're doing. And I'll sort of wind up with telling you the kind of new stuff that we're doing with aircraft, since that obviously is an interest here. Next slide. So we design, build, and operate robots, land, sea, air, and space. Next. We develop and operate these systems. We provide robotic-based services for customers, clients, and our collaborators. Next bullet. And these are the kinds of stuff that we do. It's a student-based program. We have students that are active in the program anywhere from freshmen to doctoral students, and they work on the same projects. They're all doing a different part of that project. But it's all mission-driven. And it's very hands-on. You can see up in Lake Tahoe, we're putting an underwater robot into Lake Tahoe there for some scientists for U.S. Geological Survey. This is a shot of our Mission Control Center on campus, and we control a whole line of NASA spacecraft, so it's my students in the lab that do this. Everything on the ground, all the communication stations, the Mission Control Center, the software, sending the commands, getting the telemetry back, all students. And again, freshmen through doctoral students. We build spacecraft. Here's us operating a spacecraft in the NASA Mission Control Center. Here you can see a ham radio contact with the satellite with a little 7-element Yagi, and they're trying to figure out how do we figure out how to point the antenna over time. And when I did it, when I learned how to do it, I never used what they did, but they all whipped out their smartphones and strapped on downloaded apps for compasses and inclinometers, and that's how they measured the azimuth and elevation. And they had sky trackers, and I learned a whole new generation of technology just watching them do a tried and true hands-on exercise. Next slide. Here are our customers. These people pay us to do these things, and the important thing is they pay us a second time. Okay, so we don't blow it the first time, and the fact that we're providing services to companies and agencies, not only do we have to do, it sort of ups our game in terms of the quality of what we do, but the students are involved in providing these services. They are the face of our organization to professionals, and so that means that they have to learn how to act in a professional manner as well, in addition to supporting with engineering and everything else. Next slide. We bring in on average about $500,000 a year of paid missions in order to do this kind of stuff. Next. And they work directly with the customers. They help define the services. So sometimes someone will come to us and say, I want you to do the following. Sometimes that's exactly what we do, but the students also learn to ask, why do you want that? And sometimes we propose something that's completely different because we get a better idea of what the customer wants and what the customer thought they wanted to begin with. And we find a more cost-effective way to bring them the value and to spend their money. They have to maintain and operate the systems. They have to do the planning and budgeting and management. So you can see a lot of stuff other than just the hands-on engineering. They learn how to run an enterprise in order to do this kind of stuff. And the last one on this one is, next slide. We just got recognized by the National Academy of Engineering for bringing a lot of these real-world kinds of capabilities into a standard engineering curriculum. Next slide. So just a few snapshots here. One slide on the marine side, sort of one end of the spectrum, if you will. A lot of different kinds of beasts that exist in the marine world in terms of robotic devices. So we have underwater robots. You can see up in there in the left-hand corner. You can see these are tethered. So they're a big long tether comes up to a boat, and our crew sits on the boat. And it's very much like a video game, very interactive. The robots have a camera on it and lights, and so there's a display. Usually the display is small, and you're on a boat and it's rocking, and the students there with joysticks, and it's like you're driving in a virtual world. And you have a scientist breathing over your shoulder, saying "Follow that fish" or "Pick up that rock." Very interactive. Another kind that I don't have a picture of, but this is the tail cone, which is really what we're specializing in. They're autonomous. They don't have a cable that comes back to the surface, which means you have to program them. You can't just arbitrarily guide them with a joystick and send them arbitrary amounts of power. So they tend to look like torpedoes. They're very hydrodynamic, very energy efficient. and they're automated, and things go wrong on these quite often. And so we have been working with Monterey Bay Aquarium Research Institute and NOAA to redesign the standard tail cone that goes onto these, because we're putting these under the ice in the Arctic. And if you lose one of your thrusters on one of those things, they're never going to come out. And it's easy to lose a couple $1 million that way. So, so fault tolerance is something that we have to learn to design into these robots. We have a little fleet of kayaks, which is all I can afford at this point. But we've got 10 of them, and they go out and they do collaborative missions together. And I'll talk a little bit about the multi-robot stuff here in a few slides. This is a weird beast. This looks like a pontoon boat, but you'll notice the pontoons are submerged. So this is actually called a swath design. The water line hits the struts, which means it's very, very stable in pitch and roll. And we like that because this creates underwater maps. And so we create topographic maps underwater with a nice sonar that's mounted up here in this hub. And this runs all day. So we can tell it an area to map, and it figures out its path, and we say it mows the lawn. It just goes back and forth all day. It's incredibly boring, and that's why we want to automate it. So if it works well, then we're sitting over here enjoying ourselves. And when it stops working, we have to come out and pull it back to shore. Next slide. So some of the stuff that we do with this is a number of years ago, we actually were part of a discovery up in Lake Tahoe of evidence of a tsunami in Lake Tahoe that we made with some of the geologists we work with. And we saw these boulders that were like ripples in the sand, but ripples in the sand of a tsunami wave. These are 50-ton boulders. We went back a couple of years later with that boat. So we saw them with the yellow robot up there. A couple years later, we went back and mapped it with that boat. Here is us trying to put a map together of Emerald Bay over time. And this is something that they don't have good data of. They have for the rest of the lake, but it's very hard because of the mouth of Emerald Bay to get a good mapping boat into Emerald Bay because it's too shallow. But that works in about a half an acre of water. So we're filling in the blanks, is what we say. All the interesting things that goes on in the world of marine is in the blank spaces on the maps. It's the first 10 meters right off the coast and shallow waters. That's where a lot of the anthropomorphic effects of man on the environment and fisheries and things like that tend to go. So we have kind of a niche there. Next slide. Other end of the spectrum, stuff we do in space. So here are a couple examples of satellites that my students have built. Everything from a hockey puck size spacecraft, you can see it in the upper right hand corner, to larger stuff, sort of computer monitor before the flat panels came out, computer monitor size spacecraft. And we've done a number of these. We continue to do these. Next. And then another flavor of this, the other side of the coin, is we run control systems for a series of NASA spacecraft. And these NASA spacecraft are about the size of a loaf of bread. And we've been working with NASA Ames Research Center for 10 years now. And we have done 6 missions with them. And in some cases, we've actually had a significant role in building the spacecraft, and that's fun too. But remote control is really what we do. And so here's our on-campus mission control center. This is, when you go up 280 and you see the very spectacular dish there up by the SRI dish up at Stanford. That's not it. This is the dish that would be very spectacular if the big one wasn't there. The big one captures your eye. Yeah. This is the one you could also see if you weren't staring at the big one. Okay, so we've used the big one, but this one wasn't working, and so we cut this off. And this group of students redid it, put it back on, redid the control system, got it up and running, and we started tracking these little satellites with this very large dish. That's an 18-meter dish. And it's actually a gun turret from a Navy vessel. It turns out that a 3-meter dish works very nicely, and now we have 5 3-meter dishes that we have at various places that we log into through the internet, and we control from this room here on campus. And so here's a case where everything on the ground is being done by students, and in fact, we have 12 satellites, NASA satellites, launching in the next year. And we're doing all these, and we have one actually launching on Tuesday. So better this week that I was here than next week.
Where do they launch from?
All over the place. So Tuesday is going to be out of Wallops Island. We have one going in January. There are going to be 2 going from Kodiak, Alaska, to launch at the same time. There are 2 that are up there now from previous launches that we continue to operate. When I say operate, I mean they have experiments, and the students run the experiments. They have procedures, they send commands, they get the telemetry back. They check the telemetry for state of health. They take the data products, which is the status of the biology, and do sort of level 0, level 1 level calibration and data processing, and create them and make them pretty pictures and things like that. And then they send that off to the NASA scientists. And so we run the mission itself. And then everything on the ground is our responsibility. We own it. We developed it. Our students built it, and we have to maintain it over time. Yes, sir.
What type of orbits are you in? Polar, equatorial, and multi?
A little bit of everything. So we've had a near equatorial orbit, which was out of Quaj, and so had to find students to send to the South Pacific. That was tough.
Yeah.
That's tough duty. And that's a little desolate. So they're doing nothing but working, but having a good time at it. And that was a mission that it was low Earth equatorial, so we couldn't see it from here. And so we had to send them there, and they packed a 3-meter parabolic dish and all the control equipment, and they ran it from Kwajalein Island, actually one of the atolls right next to it. Most of the others, our stations tend to be across the country in the United States, and so we can run them. So anything out of Cape Canaveral, Wallops Island, we've had 3 launches out of, and then Kodiak, Alaska, or Vandenberg is the other typical place that these things go out.
But those are polar.
So we've had polar, and we've had 40-degree.
Kodiak and
the Kodiak is polar. Yeah,
they're polar.
Yes, yeah. So 65-ish, and then really where most of the launches are going these days is a space station orbit. And that's very low, very, very low Earth orbit. So those tend to deorbit probably in 6 months, 9 months kind of thing. Very short duration, that's right. At about 53-degree inclination.
Who provides the launch vehicles?
They get them anywhere they can. So sometimes it's the launch next week is an Air Force vehicle, and sometimes it's a NASA contracted vehicle. The one in January is going to be SpaceX, so it's a commercial launch vehicle.
So these are piggybacks.
These are all piggybacks, that's right.
Okay.
So they're smaller things. They tend to be put into little ejectors and popped out, things like that. So anyway, the previous slide was marine, underwater to outer space. So next slide. Just a quick framework. So the best way I can put together this kind of thing, I need to find a way to do interesting design projects because we're teaching engineering design. And a lot of that's at the undergraduate level. But I have a lot of graduate students. I need to do engineering research, so there needs to be new and more sophisticated stuff that we do. And we want to build robots, and we want to take them out in the field, and we need money to do all that. So an ideal sort of situation is somebody has some money to run a mission, and it means good design. And so the process of what do you need, and we'll develop the mission and we'll build the robot, that's kind of a design process. But if there's some new technical twist that is necessary that we can't just buy off the shelf and we have to develop it, then maybe some graduate students are involved, and maybe this is a master's thesis or maybe more, and we're developing the technology and we pop that into maybe some subsystem or the way we control the robot. But if we can unify those two things and then go conduct the field operation, the best part is usually they don't pay for the robot. They pay for the data. They pay for the map, or to manipulate something underwater, or to get the data from the payload in space. And so we get to keep all the stuff that we build, and that allows us to do the next mission at a cheaper cost and at a better schedule. And sometimes we use them as is, and sometimes we morph them, and sometimes we say, well, we need to build something brand new. So if you hit the next few slides, so you can see design education over here, research opportunities. We're providing mission services to somebody here, next one. And all the things that we talk about in a university environment as being sort of good stuff, this allows us to do. We can integrate research and education. We can stimulate graduate school interest of undergraduates. They are working right next to master's and PhD students. They see that in action. And a very natural way to incorporate collaborations with external enterprises into our education program. Next slide. Brings in the money. We get to keep the goods. Next. Okay, so a little bit about MultiRobot Control, and so this is kind of an introduction, and we'll go into what we do and how we play with all our robot toys. So next slide. So one robot is good or more better, and so there are certainly some benefits. At the very least, it's redundancy. And maybe you can do a divide and conquer strategy where you can say, well, if I need to map a field, well then If I have 2 robots and one robot will do the left side, one robot will do the right side. But what I'm really interested in is when the robots go out, you don't just divide and conquer, they work together. And so the notion of sort of distributing the functionality you need to do a mission across multiple mobile platforms, whatever that happens to be. And maybe they're all the same, but maybe you have a plane and a boat and somebody that goes on the land, and you exploit all those kinds of capabilities that they bring to bear on whatever your mission is. So next slide. That all sounds great, but it's hard to do. That's one reason why you don't see a lot of it. This is us just charging our robots, trying the logistics of, well, did you charge that one? I thought you plugged it in, and this is just 5 robots, and it's a nightmare. So there are a lot of challenges to do this, much less get them working out in the field for 10 minutes at a time so you can get some data. Next slide. So you see, there's certainly cases where robots are quote unquote working together. Next. But these tend to be pre-programmed, sort of centrally synchronized things. And although there is some interesting work being done in certainly an industrial robot environment where this isn't quite the case, a lot of times one robot really has no knowledge, so to speak, of what the other robots are doing. And if one robot breaks down, the other robots, unless they're told otherwise, would just merely continue producing product and handing stuff off to the one robot that isn't working anymore. So there's no real-time reactivity among these things. So what we're interested in doing is trying to use more than one robot to bring value, but we're really interested in the cases where, sort of in real time, they figure out what they need to do and they can be reactive to each other and to changes in the environment. That's the kind of challenge that interests us, and it interests me intellectually in terms of my research students, and it means we get to build a lot of robots, and so that's a lot of design projects. Next slide. There are some interesting previous work out there. So this is work done at SRI, and they had 100 robots. They call it Centibots. And they marched down a hallway. But again, this was kind of a divide and conquer. They coordinated to figure out who would go in what room, then they would individually map the room. Then they'd come back at the end and they would sort of cut and paste their maps together. But the act of mapping was still a one robot kind of activity.
We call those students.
Yeah. Next. Really interesting work. I don't know if you've seen Robot Soccer, but you ought to YouTube that. And it started off with the Sony Aibo dogs. And then they have land robots, wheeled robots, but now they're using little humanoids, and they go about 5 centimeters per second, so they're pathetically slow, but put it on fast forward and you'll be impressed by what some of them do. And so this is a competition environment, but a lot of universities are really studying, what does it mean to be a team and to collaborate and, roles in a team environment, and, trying to understand that and codify it in some sense. That's kind of an interesting thing that's going on. Next. Another example is here, swarm robots, and I tend to, I don't consider myself doing swarm robots, and I've got a little bit of heartburn with the term. I think this is beautiful, really interesting work, but the typical thing that you hear people do when they talk about this is they'll say, well, we had 100 robots, and they're all very simple, and we're interested in having very simple rules and see how they interact to get sort of the collective behavior. And it was great. You wouldn't believe it. We programmed this very simple rule, and you wouldn't believe what happened. Here's what the group wound up doing. That's fantastic. That's very interesting. But that's the last thing you want in engineering. The last thing you want in engineering is to not have any idea what's going to happen when it happens. It's science. It's a study of this kind of thing, and I think that's beautiful and wonderful. But the notion that it's largely uncontrolled, and really what these people ought to be doing, at least in my opinion, is going backwards. If they would say, here's what I want the collective group to be doing, what is the simple rule, that would be a really fascinating kind of thing. That's an engineering project. Right now it's more in the realm of science. It's very, very interesting science. I just happen to have a different interest, that's all. I listen to these guys, I watch their videos, I attend their talks, but it's a different kind of problem. Next one. So, here's the kind of stuff we're doing with the sorts of things you've seen us building. Next slide. We want to do real-world tasks. Okay, so we're driven by wanting to get out. I don't want to just spend my time in the analysis and the simulation. Real-world tasks. I like this idea of multiple robots, and so I think that the reason you want to do that is you want to do tasks that require a baseline. You want to spread these things out. If you could do everything in a small area, why not just have one big robot? So We're trying to find applications that need spatial distribution and where these things need to tightly interact. So if I just say, you go left, I'll go right, we'll go individually do our things and come back later, there are a lot of applications where that's a great way to go. I'm just looking for other applications. And so we have not done this application, but the best simple example that I could give you would be, imagine doing stereo vision. And so when you do stereo vision, you have two cameras, and they usually are in one block, mounted about the same distance as your eyes, and you would put them on a single robot. And that's the way you normally do it. And so I don't know if this is useful in terms of stereo vision or not, but imagine taking the individual cameras and putting them on different robots. And now you could vary the baseline. Okay? Now, if that brings value to stereo imaging, this is something that ought to be pursued. I don't do stereo imaging, so I don't know if that brings value. I think there's some interesting things you can do with it. But the point is, that gives you the idea that it's the stereo image, which is the product, and I need to coordinate those two robots in order to properly produce that product. I need to know the baseline, they need to be facing the same locations, they have to work together to figure that out. And so that's an example of what I'm interested in doing. Okay? That's not me. Okay.
We're in a fire station.
Next slide. So, some of the things that we've been working on, and we've done some demonstrations in the field, demonstrating some of these capabilities, and a few of them we're starting to get contracts for in order to provide them at a professional level. So, tracking objects. You can imagine a radar and something flying by and you want to find its location. Well, if I do that for multiple points, first of all, I expand my workspace, but if I move them along, I can also find the optimal geometry by which to create the best possible tracking estimate. So that's one. Sparse antenna arrays. We had a small business grant on this where imagine putting different antenna elements on different mobile robots and you can change the shape of your virtual antenna and therefore you can sort of on the fly mechanically change the characteristics of your antenna and then you can use beamforming to electronically steer on top of that. So the combination of the two I think is interesting. Physically escorting, that was the first thing we did, or guarding. You invert that and you're hurting. A lot of people who are interested in that kind of stuff, that is relatively easy to do at this point. Manipulating and transporting objects that would be too big for any one of the robots to do. And a lot of times what you see robots that are sort of, move something along, but they often don't realize that the object is there. They're just kind of moving and it just so happens that they're pushing something in front of it. And so we're doing a version of this where we actually sense the forces, and we're doing force control in one dimension into the object being pushed, but then we're spatially controlling so we can apply torques. And you can imagine moving a big object with hinges, and you want to move it from one location to the other, but maybe manipulate it at the same time. That's a pretty challenging kind of thing, and we want to try to automate that. And so on and so forth. So this is the kind of stuff that we're working on, and we're using these robots that my students are able to build in order to explore these kinds of things, trying to get them to be sort of cost effective for other people to use. Next slide. Just in terms of the architecture, closed loop control, for those of you who know anything about it, the notion of you sense something, you decide what to do, maybe what you sensed is you're not at the altitude you want to fly, and so you take action. So in a wheeled robot you might say, I want to go a certain direction, where am I need to turn my motors, do actually turn the motors and the wheels run and your robot is now driving to where it needs to go, a kind of a basic navigation problem. If you go to the next slide, you can see how we're starting to piece this together. So I may have 3 parallel versions of these if I'm running a group of 3 robots. And the next slide. What we try to do is we call that a triangular formation. We tend to use a geometric representation of this, and we want to say something like, well, I want the geometry, I want the cluster of robots to drive north at 5 miles an hour. I want them to be an equilateral triangle with an edge of 10 meters. And I want them to spin at the same time. And we call that the Frisbee maneuver. So the cluster goes and they rotate as it goes. It's very easy for me to state that at a geometric level, but what the robots do is actually pretty complicated. And what the wheels on the robots do is very complicated. But math gives you all that. Okay, so we have mathematical transforms that if I say what I want at kind of a high level, geometrically what happens, I can derive what the wheels do, and I can do that in real time, and if any of them are a little too slow, the others can compensate for it. Okay, so they're interacting with each other as they go. And then we can put another layer on it with the next slide, which is, I really don't really care about the geometry. I want the geometry because I want to do an application. Okay, I want to map someplace. And so now we have another mathematical transform that relates the application to the geometry. And so I can say, hey, I want to escort the ship. And here are the parameters of escorting or protection. Describe it in the language of the application. And I have math that says, therefore, the geometry must do the following. Therefore, the robot must do the following. Therefore, the wheels must do the following. So this is kind of the math that's under the hood of these systems that we're building when we run these experiments. Next slide. So these are just plots, but this is data of real experiments. These are real robots that have been moved around. So the basic maneuvering idea is 4 robots kind of in a square, and you can see they have little tails that kind of give you an indication of the speed that they were had when we took the snapshot of data. And we did a basic maneuver where we said, maintain your formation and go from the center down here. And you can see they start to move kind of small multiple there, 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 and then they stop. And then we said, move back. And so now they start to move back. But as you move back, expand. And so you can see they're expanding at the same time, and they get to their location, and they're bigger now. And so you can mix and match these geometric sort of commands. Here, we do the same thing. This was, again, these are real robots. And we said, drive around in a triangular formation. But we have to avoid obstacles. And there are a couple different ways you can avoid obstacles. You could sort of break ranks. It used to be in the military, so breaking ranks was allowing somebody to walk through your formation. And so maybe everybody kind of jostles a little bit. Or you can pretend that you're one big virtual body and everybody moves together to get out of the way. And so this is the case where they move together as if they were one body and they don't allow the target to kind of go through the formation. You can do either one. This was the first time that one of my students got it to work for the entire formation moves together. And so basically we start here, we want to go up above, but we don't want to run into the object. And you can see it starts to move, realizes the object there, and they all move together to move around the object. Next slide. Here's an escort. Again, this is a real piece of data. This was a boat. These were our kayaks. We did not control the boat. We just sensed where the boat was. And we told the kayaks, maintain a standoff distance, sort of be evenly spread around, and as you do it, rotate. And so the boat, which is the star, kind of moved around. We knew where it was going, and it was up to the controller to basically tell the boats how to move. And you can see that slowly but surely, they're maintaining formation around the target, but you can see the blue one, they're all circling as they do that. Again, it's very simple to express that using the control approach we have. The next one, here's data of what we call dynamic guarding. So the idea here is I'm protecting this, and you can see in this case 4 robots that are around it, and they're just kind of hovering. We didn't say patrol, we just said kind of maintain position. So they're just kind of staying in their position. And then here comes a threat. And the threat gets close, these guys move over and create a wall as the threat gets close. And they establish a wall, and then when this moves away, they circle back around. Okay, a fairly complicated sort of maneuver in terms of what you have to tell the robots to do, but you can very easily explain from an application perspective what you want. Surround the robot. If something comes close, bring everybody together, form a wall, stay in between the target and what you're trying to protect and where the threat is, and when the threat goes away, kind of go back to your normal position. And the next slide is, here's what we actually did. We took that mapping boat, because we were creating maps up in Lake Tahoe, and the last thing you want is someone charging it with a speedboat. In Emerald Bay, that's exactly what happens. Anything interesting in Emerald Bay, boaters will approach it at very high speed. So then we decided, well, we put a dive flag up, which says, stay away. And it turns out that attracts them faster. And so then we put signs on it that said scientific instrumentation, even faster. Okay, at some point we're going to put radioactive kinds of warnings on it. But what we did, this was kind of interesting for us because we never thought we were going to do this. We had one project which was build some interesting thing that sort of cost effectively made maps. But we don't want big waves right next to this. And so we wound up using a whole other project, a different group of students in the lab, and said, well, why don't we protect our own asset? And here you can see they've actually kind of come over to one side because
there's a speedboat sitting over here. And when the speedboat sees the kayak sort of coming at them, they actually will slow down. So the closer they get, the tighter these things get. Now, at some point, the speedboat could outmaneuver the kayaks and we'll lose. But it was an interesting way to combine two completely different directions in our lab to actually bring ourselves benefits so that we had a stable platform to create the maps. Next slide. So we're doing things with transport. So you can see, what does it mean to collaboratively or cooperatively move an object? And I'm not sure what it means, but I think at the very least it means you don't break the object as you move it. Okay, so if the two robots are just kind of going on their own, it's very possible that you're going to have big forces or torques in the object. So this was an example of moving the object, and there was no force or torque or strain implied on the object. And in fact, they did the frisbee maneuver. We said carry the object down the hall and rotate as you go, and have no forces or torques implied on the object other than to transport it. Here's a case where for little tiny bots, that's just a piece of styrofoam on a whiteboard. We always start out in sim, then we move to tabletop robots, and we do sort of parking lot robots until we go out in the field. If you go out in the field with the boats, or you're on a satellite mission, then the money and the resources and the time goes up. So we want to make sure our control techniques work. So we start off in the lab, and here's a case of these four things. Moving that around without rotating it, and then also rotating it as they did it. Okay, and again, this is us trying to learn what it means to manipulate and transport objects using more than one robot in a smart way where they're talking to each other while they do it. Next one. This is kind of the last example. This is one that we had some really nice experimental data up in Lake Tahoe. We keep going back to Lake Tahoe. It's just really tough duty. We may be taking this technique. We have some meetings in January down to the Gulf for sniffing out oil spills. So the concept here is imagine something, so some parameter. So if you read our very esoteric journal articles, we speak in very general language, like a scalar field. But imagine an oil spill, okay? And the concentration level is high here, and you can sort of imagine these as being contour lines. And so this could be oil, or it could be anything of interest that I could put a sensor at a location and measure. A contaminant in general, whatever you care about. Thermal gradients. And so the idea here is, can we just drop a couple robots in and say, go find the source of the pollutant, or go find the high spot, or the low spot, or go to a concentration level and trace out the concentration level, because maybe that's the danger level. And in fact, maybe have a bunch of them follow each other, and you set up a perimeter for guarding, and you say, here's the perimeter of the safety zone. So this is a great example, because you need to be able to sense across the field in order to figure out how to do this. And so the idea is, we drop these robots in, and we don't know where, or if there even is anything of interest out there, and we say, just go in some direction, and they're all sniffing for oil, or the contaminant, or whatever they're looking for. And they're all exchanging this data. And right now they're all saying, well, I have nothing, okay, plus or minus a little bit of noise. And at some point, this guy says, well, I still have nothing. This guy says, well, I have more than nothing. I've got 10 units. This guy says, I've got kind of 20 units. And they're sharing this data, and they realize, well, it must be somewhere in this direction. And so they'll turn, and they'll drive, and they'll trace what we call the gradient. The gradient is the direction of maximum increase. So if you hit the next slide, they compute the gradient, hit the next one, and they ultimately drive to the max. And when they get to the max, they just kind of hover here. And there are a lot of variations on the theme. I can go to the maximum, I can go to the minimum, I can go to a certain level, turn 90 degrees, and I can track the level. All sorts of really interesting things. And these have very practical applications, like find the source of the pollutant. Next slide.
Find the size of the lift.
And the size, and create a dynamically changing perimeter for safety, to keep people away, all sorts of stuff. So we did this with our kayaks. And we actually did it for our geologists who wanted to find underwater terrain features, which is a kind of a different application, but this worked just beautifully. So if you hit the next one, here we had previously mapped Stevens Creek. This is Stevens Creek Reservoir. I don't know if you've seen Stevens Creek Reservoir now, but the blue starts about here. There's no water left in it. But for those who are familiar, here's the boat ramp. okay, when you come off the
Yeah.
Highway 17. And so we had already mapped it. So we already knew what the terrain was. In this case, the scalar field was the depth at that point. But this is where we practiced. And so what we did was we went into contour driving mode and we dropped the kayaks here. And the kayaks, we didn't give them any knowledge of the map. We just said, hey, you're going to try and find the average depth of 15 meters or something like that. And then we want you to follow that contour. And lo and behold, they went all the way around the edge. And you can see they're trying to figure it out, but they're talking to each other. Here, we told them to go up and down the contour. There just wasn't enough room to really do it well, but they did it. It wasn't really conclusive because it's such a shallow rise. But then, once we knew it worked, we went to Lake Tahoe. And we went to an area that we didn't have any mapping data, and we just dropped the kayaks. And we said, go down the slope, and then we picked them up and brought them back, and we said, dropped them in again, and we said, follow the contour. And then we went in and mapped after the fact and crossed our fingers. And the next slide is what we got there. So here's where we dropped them in, and we said, go down, and they petered around a little bit, but they headed this direction. And then we picked them up again, and we brought them over here, and we said, follow the contour, and they did something, and since we didn't wind up mapping that area, I don't know how long it took them to kind of latch on, but at some point they latched on, and they did this, and then we went in afterwards, and we mapped it using our other boat, and lo and behold, they're descending the gradient, and they're following the contour. And so this is the first time, this was last summer, we're now doing this in the field, the messy field, okay, where nothing goes the way it goes in simulation. And we have a technique now, a technique that works, and now we're putting different sensors on it. We're putting oxygen and nitrogen sensors on them, because that's how you find anoxic areas in the ocean, and that's where you get fish kills and harmful algae blooms, which is a big deal. We can put oil sensors on them of some sort. I don't know exactly what that looks like, but that's what we're going out to the Gulf in January to explore with BP of all the companies. And we're trying to figure out, we've got this interesting technique, it's interesting academically, but is there some real benefit that we could bring to somebody by turning this loose in some interesting way, and we're trying to figure that out now. Next slide. So what's in the future? So we're flying quad rotors. We're doing experiments now where we have multiple robots working together, but some are flying, some are on the ground. I have a building out at NASA Ames, which is, for any of you who are ex-military, the old Navy Home and Garden Center. I don't know if you're familiar with that, but it's been gutted and it's leaking, and there's probably all sorts of carcinogenic substances in the roof and all that kind of stuff. But it's our building now, so I can brag about it. It's a dirty workspace, and we have an indoor robot play area there, and that's where we're running some of this stuff. And right now it's because it's all really cheap equipment. These are the little Brickstone AR drones that you can get for $300 controlling your iPad, but they don't, they're not worth anything outdoors really. So, but indoors, we're playing all this, and we have an indoor tracking system that mimics GPS so that we can run our experiments and make sure we're good before we go outdoors. Next slide. We're going to take this. We're now doing MultiRobot Control, spatial geometric control with underwater robots, tethered underwater robots in close work areas. To my knowledge, has never been done before. This is what you need to have multiple robots work together without 1,000 people on the surface to do things like cap oil wells and to reclaim areas on the ground that have just been littered with various things. And so we want to do manipulation with more than one robot. And these are robots that we operate professionally. Next slide. We're going into space. And so this is the Spheres platform. We did not build this. MIT and DARPA built these, but these are now available, and we have been offered a test flight with these 3 little bowling ball-sized spacecraft. This has got to be the most expensive test bed in the world because the astronauts literally hold the robots in their initial conditions at the right locations until you say go, and then they let go. And you have like 2 minutes to fly around and demonstrate your technique. So we've been approved to run an experiment, and it may take 2 years to get there, but this is the direction we're going. We're using the exact same technique on a completely different kind of robot. Next one. And so, we're interested in aircraft, and that's another reason, other than Godfrey telling me I should come and say hi and see what you all are up to.
there might be some interesting angles here. So we have done UAVs for quite some time. We were doing it 10 years ago before the FAA said stop, and we had, follow the leader kinds of autopilots and things like that. And then they said, we're uncomfortable, we're not sure how to regulate this technology, and so we created everything, figuring, well, it'd take a year or two for them to figure out what they want, and then we'll be back out flying again. So, a decade later, we think there's now a law that says there needs to be another law in 2015 to allow us all to do this. So I don't know if another law will be passed saying they can delay the first law, but we want to be ready. And when I say that, what I mean is we want to be ready to do the same things we're doing with the marine robots and the satellite stuff with UAVs. We want to support professional class services, whatever that means. And I don't know how to do that yet, and we're going to try and figure that out in the next year and a half. So we want to provide services, but we want to do it in a way that it's interesting design projects so our students learn. If there's an interesting technology twist, then I could get some graduate research. At the very least, I want to have some multi-UAV kinds of things going on because that sustains our multi-robot area of research. Next slide. So to do this, we are now in the process of getting new platforms. So we've got some of the Octo 3D robotics, octocopters. We're using the 3D robotics RU plane just as trainers. We have an order in on a Maha, which is one of the planes out of conservation drones that can give you a little more than an hour flight time and more than a kilogram of payload. And with the idea we can go out in the field and sort of do more endurance kinds of things. These are all electrically powered. So we're getting new platforms. Next slide. We're getting new payloads. So everybody will have a GoPro attached to their quadcopter, so we'll do the same thing. The ones who are into it, and maybe some of you have one of the cameras that tags it with GPS metadata, so you can do mosaicing of your photographs. So we've got some of these. We're also picking up some FLIR infrared cameras. That's a Pathfinder unit out of the front of a BMW, but that's all I can afford right now. I can't afford the BMW. I can grab the sensor out of this front bumper though. And that just gives you an idea. That's a thermal image of a field that shows you the watering pattern. So you can see the dark stripe is heavily watered and the other area is not. And so any of you who've done aerial imaging probably know more about this than I do. What we want to get to is be able to afford some multispectral imagers. And we've got, I think, a plan on doing that. But we want to go sort of beyond what a good hobbyist would have to get some of the payloads that would get us the ability to get some really unique data products.
How big is that FLIR?
That's a couple hundred grams, and it's about that big. It's not what I would want, but it's all I can afford. FLIR has a unit they call the Tau, which is much lighter weight and much smaller and better, a better
Price?
sensor. eBay, I got it for about $1,600.
1,600?
$1,600. Most of them are running in the 25 to 4,000 range, and occasionally you can get a deal.
Yeah, I bought a $3,000 FLIR last year for my company. So they're
From
expensive.
FLIR or?
From FLIR.
Yeah. So this is used and it's a little beat up, but right now we're not providing those professional services. We're trying to learn how to do it, and I need to do some demonstrations before I can move forward with better stuff. So this is kind of where we're at right now. Interesting thing, when we started our marine robotics program, our first customer was an archaeologist who was a professor at our own university, and he wanted to run a mission with a student to find a lost whaling fleet, which we thought was ridiculous, but it got us money to build our first professional class underwater robot. Long story short, we found that whaling fleet, and it was turned into a Discovery Channel special. So what do I know? But the interesting thing was, we found our first customer in our own backyard. And so I've contacted our facilities person and said, look, I don't know if you're interested, but we're building this program. He's all in. He's going to invest money for us to do things like thermal mapping of our buildings, to find heat loss. He wants to use it to manage the plant itself. In terms of, the amount of grass that's on the campus is unbelievable, so agricultural management, so to speak. He has even said a few things that we joked about in my lab, but we never would have suggested, which was like active shooter kind of response scenarios. So he's providing us with our first wave of funding once we can do the initial demonstrations. And if we can do that well, then maybe we can attract interest outside our school, and that's kind of how we bootstrapped our initial operation 15 years ago. So new platforms, new payloads, and then to do something with that data, I think, is critical. So the next slide is the data products. So here's an aerial image, but better yet,
This is actually a mosaic of 300 aerial images, okay? And it's not really an image. It is an image that has been applied to a 3D model that was generated from those 300 images. Okay, so this is a CAD model that you can rotate and manipulate, and you can get the digital elevation map, the topographic map from the aerial imagery, and then you can put this on top of it. You can apply it to the elevation map. So this kind of stuff, this starts to distinguish us from a hobbyist who's really into it. So I'm going to be competing with the guy with the quadcopter and the GoPro who says I can take a good snapshot for the real estate agent. And that's great. But if we can do sort of GIS certified mapping services using a higher end payload and some really nice software to do the processing, that's going to give us a little bit of advantage and will help us sort of try to figure out where we should fit. I mean, it's going to be a student operation. I want the students doing engineering. I want them running the engineering enterprise so they get all that other stuff. But there's a limit to which we wouldn't go beyond, and I don't know what that limit is for the UAV stuff. But we know what we're good at in the marine world. We know what we're good at in the satellite world. And it'll take a few years, but we'll figure it out for the UAVs as well. Next slide. So this is what I would say at the end of a talk if I was giving my graduate seminar, okay? That clearly I've demonstrated to you that building automated